A monster winter storm.
That deadly storm battering the nation with...
We are expecting things to be colder, not getting warmer.
Many people like the snow, but not the cold that comes with it. We totally get it because it can get very cold. However, as they say in the hit series Game of Thrones, winter is coming. Yes, thanks to the Milanković cycles, a global winter is coming upon the planet. Should you be stocking up on winter wares? Since this has a lot to do with seasons, what causes seasons on Earth? Wherever you are watching this video from, the season changes all year round. So where do these seasonal changes come from? A season is a time of year distinguished by distinct climatic conditions. The 4 seasons, spring, summer, fall, and winter, regularly follow one another. Each has its own seasonal light, temperature, and weather patterns. Winter in the Northern Hemisphere typically begins on December 21st or 22nd. This is the winter solstice, the day with the shortest amount of daylight. And summer with lots of sunshine officially begins on June 20th or 21st, the summer solstice, which has the most daylight of the year. Spring and autumn begin on equinoxes, which are days with equal amounts of daylight and darkness. The vernal or spring equinox occurs on March 20th or 21st, with the autumnal or fall equinox occurring on September 22nd or 23rd. Interestingly, seasons in the Northern Hemisphere are the direct opposite of those in the Southern Hemisphere. This means that our friends in Argentina and Australia see winter starting in June. In the Southern Hemisphere, the winter solstice is June 20th or 21st, while the summer solstice or longest day of the year is, you guessed correctly, December 21st or 22nd. Seasons have a huge impact on vegetation and plant growth. Winter weather is typically cold with little daylight and limited plant growth, creating a huge drab canvas. However, come spring, plants sprout, tree leaves unfurl, and flowers bloom in a profusion of colors that contrast pleasantly with winter. Summer is the warmest season with the most daylight, so plants grow quickly, but temperatures drop in autumn and many trees lose their leaves. Also, not every part of the planet gets 4 seasons per year. In fact, only the mid-latitudes have a 4-season year. Mid-latitudes are areas that are neither near the poles nor close to the equator. Now, the seasons differ more dramatically as you travel north or south. In the middle of June, Helsinki, Finland, has 18.5 hours of daylight. But before you start making plans to move there, the city gets less than 6 hours of sunlight in mid-December. In southern Europe, Athens, Greece, has a smaller variation. In June, there are 14.5 hours of daylight and 9.5 hours in December. Seasonal variations are minimal near the equator. Throughout the year, they have roughly the same amount of daylight and darkness, and these locations are warm all year. Regions near the equator typically have alternating rainy and dry seasons. Polar regions, on the other hand, experience seasonal variation despite being colder than other places on Earth. The amount of daylight varies dramatically between summer and winter near the poles. Between mid-May and early August, it is light all day in Barrow, Alaska, the northernmost city in the United States. Between mid-November and January, the city is completely dark. Now, many people assume seasons occur due to Earth's elliptical orbit around the Sun, with winter occurring when Earth is farthest away from the Sun and summer occurring when it's the closest to it. Our planet's distance from the Sun, however, has little effect on the onset of seasons. In fact, Earth is closest to the Sun or at its perihelion around the winter solstice in the Northern Hemisphere, and farthest away from the Sun or at its aphelion around the summer solstice in the Northern Hemisphere. The seasons on Earth have a different explanation. The Earth's axis is an imaginary pole that runs through the center of the planet from top to bottom. The Earth revolves around this pole once every 24 hours. That is why we have day and night and why every part of Earth's surface experiences some of both. Now, Earth has seasons because its axis doesn't stand up straight or because it tilts. We are tilted at an angle of 23.5 degrees relative to our orbital plane. This tilt is known in scientific circles as obliquity. The distribution of mass on the planet has a strong influence on the tilt of the Earth's axis. The Northern Hemisphere's large landmass and ice sheets cause Earth to be top-heavy. Imagine what would happen if you spun a ball with a piece of bubble gum stuck near the top as an analogy for obliquity. When spun, the extra weight would cause the ball to tilt. But where did the tilt come from originally? Well, long ago, when Earth was young, something large is thought to have hit it and thrown it off kilter. As a result, rather than rotating with its axis straight up and down, it leans over slightly. And by the way, the name of the big thing that hit Earth is Theia. It also blew a large hole in the ground. A massive amount of dust and rubble was launched into orbit as a result of the big hit. Scientists believe that rubble eventually became our moon. Now, the Earth's tilted axis always points in the same direction as it orbits the Sun. As a result, different parts of the Earth receive direct sunlight throughout the year. And by the way, we are not alone in this tilting issue. Other planets in our solar system tilt to varying degrees as well. Uranus has extreme seasons and rotates almost sideways at 97 degrees. Venus has an axial tilt of 177.3 degrees. As a result, Venus has only a few seasons. Now, the angle of tilt does not change over the course of a year. Take note, over the course of a year. In other words, the northern axis of the Earth always points in the same direction in space, and the moment that direction is more or less towards Polaris, the North Star. However, as we orbit the Sun, the orientation of Earth's tilt with respect to the Sun, our source of light and warmth, changes. In other words, the northern hemisphere faces the Sun for half of the year and faces away from it for the other half. The same can be said for the southern hemisphere. When the northern hemisphere is oriented toward the Sun, that part of the planet warms due to an increase in solar radiation. The Sun's rays are striking that part of the planet at a steeper angle. It's summertime. When the northern hemisphere is turned away from the Sun's rays are less direct, and the northern hemisphere cools, hence winter. If Earth did not tilt at all and instead orbited the Sun exactly upright, there would only be minor variations in temperature throughout the year as Earth moved slightly closer to the Sun and then slightly farther away. There would also be temperature differences from the equator to the poles, but it goes without saying that without Earth's tilt, we wouldn't have wonderful seasonal changes and our associations with the different times of the year. Now, seasons are in a yearly cycle, but there are actually longer cycles that affect a planet's weather significantly. These are known as Milanković cycles, and this is where it starts to get interesting. Of course, you probably have never heard of Milanković cycles. In fact, many scientists haven't either. Milanković cycles are periodic changes in a planet's orbital characteristics that control how much sunlight it receives over hundreds of thousands of years, affecting its climate and habitability. Scientists can now simulate Earth's Milanković cycles millions of years in the past and future and compare their results to evidence found in geological sediments all over the world. In fact, Milanković cycles play an important role in planet habitability. Milanković cycles are named after Serbian mathematician and astronomer Milutin Milanković, who proposed that past variation in Earth's climate, evidenced by geological sediments, were caused by changes in the amount of sunlight reaching the planet. Milanković calculated those cycles back 600,000 years, including the amount of sunlight reaching Earth's upper atmosphere, and pointed out that these changes were responsible for the periodic swings between ice ages and warm interglacials. He proposed that the ice ages occurred when orbital variations caused the northern hemisphere around Hudson Bay and northern Europe to receive less sunlight in the summer. Short, cool summers failed to melt all of the snow from the previous winter. Year after year, the snow would accumulate and its gleaming white surface would reflect more radiation back into space. Temperatures would fall even further and an ice age would eventually break out. Milanković predicted that the ice ages would peak every 100,000 and 41,000 years, with additional blips every 19,000 to 23,000 years based on orbital variations. So, what drives the Milanković cycles? The amount of sunlight reaching our planet's outer atmosphere is determined by three factors: the tilt of Earth's axis toward the plane in which the planet orbits, the eccentricity of its orbit or how elliptical the orbit is, and the so-called precession of the planet's axis. As Earth spins, its axis slightly wobbles, pointing in different directions over time like a spinning toy top. The gravitational forces of other planets in the solar system, as well as the Sun's and Earth's moon's pull, all have an effect on these parameters. Each of these parameters changes at a different rate, but because astronomers know our planet and its neighbors' orbits with great precision, they can calculate the Milanković cycles hundreds of millions of years into the past and future. The first cycle is the orbital eccentricity variation of the Earth. Earth's orbit is one of the most circular of the solar system's planets. This, however, has not always been the case, and it will change in the future. These changes are primarily caused by the gravitational pull of Jupiter and Saturn, and they affect the length of our seasons. The length of the seasons is roughly equal in a nearly circular orbit, but as the orbit becomes more elliptical, the length of the seasons begin to vary. This can cause significant climate change over long periods of time. The eccentricity cycle has a very small effect on global annual insolation, the Earth's exposure to the sun's rays. It is a minor contributor to annual seasonal climate variations. However, it begins to make a difference over long timescales. The Earth currently reaches its closest point to the Sun, known as perihelion, in early January during the summer of the Southern Hemisphere, and its farthest point from the Sun, known as aphelion, in early July. The difference in distance between the planet and our Sun is about 3.2 million miles, or 5.1 million kilometers, which is only about 3.5% of the average Sun-Earth distance. As a result, 6.8% more sunlight enters the Earth's atmosphere in January than in July. However, the short-term impact on climate is negligible. However, when the planet's orbit reaches its most elliptical stage, which will happen in about 100,000 years, the difference will result in 23% more sunlight reaching Earth's atmosphere around perihelion, and this difference could cause significant changes in the Earth's climate over time. Then there are the changes to the tilt of the Earth's axis. As said earlier, the Earth revolves on an axis angled toward the orbital plane. This tilt currently deviates by 23.4 degrees from a 90-degree angle toward the orbital plane. However, this obliquity varies over time. It has shifted from 22.1 degrees to 24.5 degrees, but that happened over the last million years. The seasons on Earth become more extreme during more tilted periods, as each hemisphere receives more sunlight in summer when it's tilted toward the sun and less in winter when it's tilted away. And longer winters cause the polar ice caps and continental ice sheets to expand over time. During the ice ages, most of Earth's land could be covered in ice, transforming the planet into an inhospitable snowball. These swings in the tilt of the Earth's axis occur every 40,000 years. And then there is what is called precession. The Earth's axis wobbles in a circle as it spins. This is known as axial precession. As a result, the axis now points north toward the star Polaris, also known as the North Star, and in a few thousand years it will point to the star Kochab in the constellation Little Dipper. The axis takes 25,772 years to complete a full circle. Axial precession causes seasonal contrast to be more extreme in one hemisphere and less extreme in the other, and this effect interacts with the planet's orbital precession. Essentially, not only does the Earth's rotation axis wobble, but so does the entire plane in which the planet orbits the Sun. As a result, the planet's closest and farthest point from the star are not fixed, but move over time. Currently, perihelion occurs during the southern summer, but in about 13,000 years, the northern hemisphere will be closer to the Sun during the summer months. But are these Milanković cycles real? The most compelling evidence the Milanković cycles govern Earth's climate is that astronomical calculations match what geologists see when they date layers of sediment found in areas that once formed the ocean's bed. Scientists know that the Milanković cycles influenced glaciation because they can see it in geological records. But what do they see? Well, for example, there is always some sediment at the bottom of the oceans that slowly deposits. When there is more rain, say due to changes in global circulation, there will be more erosion and sediment of a certain type. When the climate becomes drier, a different type of sediment forms. This is how these sediments help to document climate change. Excavations have revealed that Earth has experienced at least 5 major ice ages over the last 2.4 billion years. The Pleistocene epoch, which lasted from 2.6 million to 11,700 years ago, saw the last ice age peak around 20,000 years ago. Global temperatures were about 10 degrees Fahrenheit or 5 degrees Celsius colder at the height of the last ice age when woolly mammoths roamed vast ice sheets covering North America and Eurasia. And a series of fossil coral reefs formed on a shallow ocean bench in the South Pacific during warm interglacial periods provided the first evidence supporting Milanković's theory of the precise timing of the ice ages. As the ice ages progressed, more and more water froze into polar ice caps, lowering ocean levels and exposing the reef. When the ice melted, the ocean rose and warmed, forming a new reef. At the same time, the motion of the Earth's shifting tectonic plates was steadily pushing up the peninsula on which the reefs formed. Today, the reefs form a visible series of steps along the Papua New Guinea coastline. The reefs, whose ages have been well defined due to decaying uranium in the coral, measured the millennia between ice ages. They also established the maximum duration of each ice age, and the intervals fell precisely where Milanković predicted. These Milanković cycles have serious effects on life on Earth. In fact, scientists believe that life on Earth as we know it could only have arisen due to the relatively mild nature of the planet's Milanković cycles. Russell Dietrich uses Milanković cycles to predict the habitability of exoplanets. He believes that being in the so-called habitable zone, a region around the central star where liquid water can exist, is insufficient to support life on an Earth-like planet. According to some studies, having strong Milanković cycles, particularly with large obliquity changes, may actually be beneficial to habitability. It has the potential to keep the planet from entering a snowball state. In other research, however, scientists discovered quite the opposite. With the large obliquity changes, they discovered that super-large ice sheets could form on land, which are basically permanent and extremely difficult to remove because they introduce thermal inertia. So the consensus is the more pronounced the Milanković cycles, the less habitable a planet is. To understand an exoplanet's Milanković cycles, we need to have very accurate measurements of not only the planet's orbital parameters, but also the orbital parameters of all the other planets in the system. This is because Milanković cycles are a complex phenomenon caused by perturbations from all other planets in the system, as well as perturbations from the host star and any moons that the planet may have. Apart from the Earth, Mars is the only planet for which scientists have enough data to analyze its Milanković cycles and their impact on climate. Mars experiences much more extreme Milanković cycles than the Earth. Its obliquity varies much more than Earth's, and its eccentricity varies much more than Earth's. Measurements of polar deposits taken by orbiters scanning the red planet reveal alternating layers of ice and dust, indicating the temperatures in Mars's polar regions have fluctuated over the eons. Now let's turn to our moon. Without the moon, the climate would most likely be far less hospitable to life. In fact, some scientists believe that life on Earth would be impossible without the moon. This theory was proposed in 2000 by astrobiologist Peter Ward and evolutionary biologist Donald Brownlee in their book Rare Earth. The two hypothesized that the large and massive moon exerts a torque on Earth's equatorial bulge, or the planet's widening around the equator, which stabilizes the planet's axis precession. Ward and Brownlee contend that if the moon were not present, the Earth's axis would oscillate by up to 30 degrees, resulting in much more pronounced climate fluctuations. Despite advances in computer modeling, some mysteries remain about the Earth's changing climate and the Milanković cycles. For example, according to geological records, the Earth's climate changed with a periodicity of about 100,000 years up to 1.5 million years ago. These variations would correspond to changes in the eccentricity of the Earth's orbit. Older sediments, on the other hand, reveal a much shorter cycle of about 40,000 years, which would reflect changes in the obliquity of the Earth's axis. But what caused this abrupt change is a complete mystery. It doesn't make sense because the eccentricity changes are so minor, and the resulting change in sunlight are so minor that we wouldn't expect it to happen. This means that the planet will face severe climate change in the future. We've had an amazingly consistent climate for the last 10,000 years. Agriculture couldn't begin until the interglacial period. Human civilization flourished at that time. But of course, we are messing with the climate and seriously altering the very even plateau that we've enjoyed for millennia. What happens to the climate in the coming decades could set us up for a much earlier climate catastrophe. However, that point in time would not arrive for tens of thousands of years. The next ice age could occur in 50,000 years. So does this mean the Milanković cycles are the scapegoat of the current climate change instead of human activities? Well, no, for multiple reasons. First, Milanković cycles operate on long timescales ranging from tens to hundreds of thousands of years. In contrast, the current warming of the Earth has occurred over timescales ranging from decades to centuries. Milanković cycles have had little effect on the amount of solar energy absorbed by the Earth over the last 150 years. In fact, NASA satellite observations show that solar radiation has actually decreased slightly over the last 40 years. Second, Milanković cycles are only one factor that may have contributed to past and present climate change. Changes in the extent of ice sheets and atmospheric carbon dioxide have played important roles in driving the degree of temperature fluctuations over the last several million years, even for ice age cycles. The extent of ice sheets, for example, influences how much of the sun's incoming energy is reflected back to space, and thus the temperature of the Earth. Then there's the matter of carbon dioxide. As part of the Milanković cycle-driven changes to Earth's climate, the concentration of carbon dioxide in our atmosphere fluctuated from about 180 parts per million to 280 parts per million during the previous glacial cycles. These fluctuations contributed significantly to the overall change in Earth's climate that occurred during those cycles. Today, however, it is the direct input of carbon dioxide into the atmosphere from the combustion of fossil fuels rather than climate feedback from the ocean or land caused by Milanković cycles that is responsible for changing Earth's atmospheric composition over the last century. Carbon dioxide concentrations in the Earth's atmosphere have increased 47% since the beginning of the Industrial Age, from about 280 parts per million to 412 parts per million. Carbon dioxide levels have risen by 11% in the last 20 years. Scientists are confident that this carbon dioxide is primarily the result of human activity because carbon produced by burning fossil fuels leaves a distinct fingerprint that instruments can detect. Since 1850, the global average temperature has risen by more than 1 degree Celsius or 1.8 degrees Fahrenheit. And furthermore, recent scientific assessments predict that the Earth will warm another half a degree Celsius or almost a degree Fahrenheit by 2030. In other words, this relatively rapid warming of our climate is occurring in addition to the very slow changes in climate caused by Milanković cycles. And what's more, climate models show that any forcing of the Earth's climate caused by Milanković cycles is overwhelmed when the concentration of carbon dioxide in the atmosphere exceeds 350 parts per million. Since 1750, the warming caused by greenhouse gases emitted by human combustion of fossil fuels has been more than 50 times greater than the slight extra warming caused by the sun itself. If the current warming on Earth is caused by the sun, scientists predict that temperatures in both the lower atmosphere and troposphere and the next layer of the atmosphere, the stratosphere, will rise. Instead, balloon and satellite observations show that the Earth's surface and lower atmosphere have warmed while the stratosphere has cooled. And finally, the Earth is currently experiencing an interglacial period, a period of milder climate between ice ages. Scientists believe Earth's current orbital positions within the Milanković cycles predict our planet should be cooling, not warming, continuing a long-term cooling trend that began 6,000 years ago. Let's hear what you think about the Earth entering a long ice age in the comments section below.